Okay, now we're going to introduce hypothesis testing, which is a really important concept in statistics. Let's start out with a hypothetical example. Let's suppose we have a manufacturer, a food packaging company, and they make bags of potato chips. And the bags say on them that they contain 8 ounces of potato chips. So now we have somebody come in, a customer, or maybe somebody who is analyzing this, perhaps from the Food and Drug Administration, and they buy 5 bags of chips and they weigh them on an accurate scale, and then they get the following weights: 7.5, 7.7, 8.1, 7.2, and 6.9 ounces. So notice, none of these are exactly 8 ounces. A couple of them are more and some of them are less. And so our question is that labeling accurate? I mean, would we expect them all to have exactly 8 ounces? I wouldn't think so. You just break off a little corner of a chip and it'll change, right? But is it far enough away from that we think there's a problem? So one thing that we could do is we could calculate the average, or the sample mean. This is a sample, remember? So let's find our sample mean. Okay, and remember we represent that with an X bar. And so we're going to add all of these potato chip weights. And divide by how many we have, which looks like 5 of them. And it turns out this gives us 7.48 ounces. So it is a little bit underneath the 8 ounces that's claimed on the package. Now if we would have grabbed 5 bags and their average would have turned out to be maybe 4 ounces instead of 8 ounces, I think we'd probably all agree that something is wrong. But 7.48, is that close enough for us to think there's a problem? And so questions like that are why we would do a hypothesis test. Okay, so in order to get started, the first thing we need to do is talk about the null and alternative hypotheses. Sorry about that. Okay, so in science, a hypothesis is a statement that you can test through experimentation or some kind of systematic observation. In statistics, a hypothesis is going to be a statement regarding the value of a parameter in a population, or maybe in more than one population. And in hypothesis testing, we're going to have 2 hypotheses. One of them is the null hypothesis, which we usually call H0. And this is generally a statement of equality. And so the null hypothesis indicates that any apparent effect or difference is due to chance. Okay. Then we have the alternative hypothesis, which is denoted H1, or often, or HA for alternative hypothesis. Okay, and this is going to be a statement of inequality. So in this case, the alternative hypothesis indicates that any apparent effect or difference, in this case perhaps the difference between the potato chip weights in the sample and the claim on the package, is not due to chance. So in general, we're going to think of the null hypothesis and the alternative hypothesis as complements of one another. So let's look at some possible pairs of null and alternative hypotheses. Okay, so H0 and H1. So again, H1 is often represented as HA. It doesn't matter. Okay, so in all of these, what we're going to think of is our mu0. Remember, mu represents the population mean. So mu0 is going to be our benchmark number. So this is basically what we're going to be comparing against. So in the potato chip example, that would be the 8 ounces that's on the package. Okay, and so if the null hypothesis says that the population mean is not equal to that mu0, that's what we call a two-tailed test, and that's going to have to do with the area that is shaded when we draw the curve. Okay, so we will get to that. and mu equals, so H0 is, or the null hypothesis is mu is equal to the benchmark, and then the alternative is mu is not equal to the benchmark. Okay, so that's what we call a two-tailed test. This is the most common type of test. So when you're not sure, when in doubt, that's what we're going to use. Okay, then we're going to have a one-tailed test. So in this case, notice I still have mu, that's my population mean, is equal to my benchmark for my null hypothesis, but then for my alternative hypothesis, I have mu is less than the benchmark. So this is what we call a left-tailed test. Okay, and in a test like this is going to assume that mu greater than the benchmark is not possible or of zero interest, and we're going to focus here mostly on the not possible because that's generally when you should use it. If it's of zero interest, if it's possible, you still kind of have to account for it. So the not possible is the primary situation for this one. And this one is the other one that we have here, the third possibility, mu bigger than the benchmark mu 0 for our alternative hypothesis. This is also a one-tailed test. This one is going to be a right-tailed test. And once again, the general place when you use this is when the other direction, mu being smaller than the benchmark, is not possible. There's different ways to write the null hypothesis. So remember how I said you can think of the null hypothesis and the alternative hypothesis as complements of one another? Well, if you look at this first situation, this one right here, you can definitely see that these are for sure complements, because if they're not equal, they're definitely going to be unequal, right? But if you look at these one-tailed tests, so you have to take into account for this middle one, for example, if the mu is bigger than the mu 0, well, that's not represented in either of these hypotheses. But remember how we said that that's generally used when we assume that that other direction, the mu bigger than the benchmark, is not possible. So as long as that's not possible, then these are still complements as long as the other direction is impossible. Okay? And so the particular book I'm using in this class right now is writing it the way that I have here, with the null hypothesis having an equal sign in it always, but it is possible sometimes to write it the other direction where it's greater than or equal to on the one-tailed test. And everything about how you do the test ends up being identical, so it really doesn't matter much. Okay, let's move on. So as I said, two-tailed tests are much more common, and if you want to use a one-tailed test, you have to have a rationale for doing so. Usually, and the rationale is generally that the other direction is not possible. All right, so let's see if we can write the hypotheses for our potato chip example here. So our claim by the manufacturer is that the bags of chips weigh 8 ounces each. So we want to figure out what the null and alternative hypotheses are if someone wants to test this. Okay, so our null hypothesis and our alternative hypothesis. So for the null, I'm going to call that H0, and for the alternative, I'll call it H1, or else you could call it HA. Okay, so what is my benchmark in this case? The benchmark is 8 ounces. That's the number we're comparing against. And so that means that my mu 0 is 8 ounces. So what I'm going to put here for my null hypothesis is that mu is equal to 8 ounces. Okay, and for my alternative, I'm going to put, and I'm going to just tell you right now that this is a two-tailed test, but when we get to a one-tailed test, we're going to come back and revisit this, and I'll tell you how you can tell them apart. So if it's not 8 ounces, then it's not equal to 8 ounces. So I put a inequality sign there, a not equal, or equal sign with a slash through it. So there we go. So these are our null and alternative hypotheses. So notice both of these are statements, they're not numbers. So this H0 here is a label basically saying which hypothesis it is, but our statement is mu, that's my population mean, mu is equal to 8 ounces. If you did not have the mu equals there, it would not be correct. It's important to have the whole entire statement, because a hypothesis, just a number by itself, is not a statement. So we need to have a statement of equality or inequality for each of these. Now, this is a two-tailed test because the inequality can go either direction. It's not restricted to go just one way. So as long as it's not 8 ounces, then it's not equal to 8 ounces. And now that puts us into our alternative hypothesis. Okay, let's look at another one and see if we can set up the hypotheses. Let's look at this one. So we have an example, and we have a widely accepted normal body temperature of 98.6 degrees Fahrenheit. And so a researcher wants to know whether this certain population of Native Alaskans has a mean body temperature that is, whether their mean body temperature is the same, whether it's 98.6 degrees Fahrenheit. And so we want to figure out the null and alternative hypotheses. Okay, so once again, I'm going to write down my labels, H0 and H1. What is my benchmark? My benchmark is that mu0 of 98.6 degrees Fahrenheit, right? Okay, so my null hypothesis is always going to have an equal sign. So I do mu is equal to 98.6 degrees Fahrenheit. And in this case, my mu is going to be the population mean for temperature of this population of people. So it's for a very particular group of people. Okay, and so that's what we would end up comparing if we were to actually carry out the test. Okay, and so then what's my H1 going to be? Okay, my H1 mu is not equal to this. Okay, and again, I'm going to talk next about how to recognize a one-tailed test when you see one. Okay? All right, so these are our null and alternative hypotheses. Okay, let's move on. Let's look at this one. The average amount of lead in the blood of young children is 2 micrograms per deciliter. Okay, and a city has recently changed its water supply, and there have been reports of increased lead levels in the water. And there is a concerned doctor who wants to dig into the records to find out whether the kids in this particular city have lead levels that are above 2 micrograms per deciliter. And we want to write down the null and alternative hypotheses. Does this ring any bells for you? Have y'all ever heard of the water situation in Flint, Michigan, where a doctor really did start investigating and they found that there was a problem? Okay, so in this case, what is our benchmark? Our benchmark is that 2 micrograms per deciliter, and you really should have units with that. Okay, and so now let's write our null and alternative hypotheses. So H0 and H1. Okay, and don't forget you're going to need a mu for each of these because we need to turn each of them into a statement. Okay, so the first one's easy. Mu is equal to 2 micrograms per deciliter. Okay, now here's where we need to be careful. Look at your alternative hypothesis. So what are we trying to find out? Let's go back to our problem. So the doctor wants to dig into the medical records and to find out whether the kids have blood levels above 2 micrograms per deciliter. This is what tells us that we have a one-tailed test. Okay, that above right there. So basically this is steering us in a particular direction. Okay, and because of the situation, this doctor seems to feel confident that there's not really any chance their lead levels are going to be low. If anything, it'll be high, or else they'll be the same. So this is an example of where we would use a one-tailed test. So I'm going to make this a greater than symbol, and then I'm going to write down my benchmark again. Okay, so basically the way you recognize the one-tailed test is that somewhere in the problem situation, in the problem description, it's going to steer you in a particular direction. So the researcher wants to find out if the levels are above 2. The researcher wants to find out if the weight is below 75. So there is some kind of a direction, and it seems reasonable that it would not go the other direction. And I think that's the case here. I think a one-tailed test is very reasonable here. Okay, let's go back at the 2 previous ones and just look at them again so that you can see the difference. Okay, so let's look at this one. Does it say anything about knowing whether the body temperature is above or below this benchmark? No, it just wants to know if it's equal. So there's nothing steering us in a particular direction. If nothing is steering us in a particular direction, the default is a two-tailed test. So that's what we're going to do. Let's go back to this one. A customer wants to determine whether this claim of an 8-ounce package size is true. Again, there's nothing steering us like they think it's more, they think it's less, the other direction's impossible. And so again, a two-tailed test is the correct choice there. So this one's also a two-tailed test. Okay, and as we work through problems, we'll see more examples of that. But this one, that above, is steering us in our direction.